which is an interesting area to look into. And let's see what Bill is going to tell about how machine learning can improve those predictions. To you, Billy. Thank you.
Thank you so much for having me, Arbesh, and for the introduction. It's a real privilege to be here and talking. So basically, being able to predict drug properties is important. So properties that would indicate how good the drug is or how good the potential drug would be, being able to predict that would save time in drug discovery projects. And especially because the preferred route of drug delivery is oral, it would be good and useful to be able to predict whether a drug can permeate the gut membrane, because you take it as a tablet, it goes through the gut into the blood, or it can even need to permeate cells to reach intracellular targets. So there are models of membrane permeability for small molecules, and the mechanisms of membrane permeability for those molecules are well understood. In particular, the rule of five, Lipinski's rule of five, works well for small compounds, but there is a clear need to be able to predict membrane permeability for larger compounds, and that's what we really wanted to do. And is it changing? There we go. Just took a while. Whoops. Yeah, there we go. Sorry about that. So this project really started at MIPS when I was doing my PhD in collaboration with Ray Norton and the SPSB group. So they had a compound like this, which had a very high affinity for its target, SPSB, but it was basically membrane impermeable, and any change we made to this compound did not affect permeability and often abolished activity. So for this particular macrocycle of this large cyclic compound, it would be useful to be able to predict membrane permeability to guide synthesis. So macrocycles often have high binding affinity and specificity for their target, but they're also often membrane impermeable, often due to large or polar interactions that are present and make it highly potent to the target. So the ability to predict membrane permeability in general would be useful for drug design, especially for macrocycles, especially since Lipinski's rule of five typically fails for these compounds. So just with reference to this diagram here at the top, often the macrocycle will exist in certain conformational states in water that allow for hydrogen bonding with water. And while existing in the hydrophobic membrane, there's like a puckering of the molecule. So the hydrogen bonds or the polar groups or the charge groups are shielded by intramolecular interactions. And to model membrane permeability via this mechanism, Rezai et al. In 2006, so they performed conformational searching in continuum chloroform and water models, and they found that the change in solvation for energy between the hydrophilic and hydrophobic solvent correlated to permeation rate. In a more detailed study with a larger sample size, Guimarães et al. Took permeability data from a pharmaceutical database, and they had access to 35,000 compounds, many of which existed beyond the rule of five chemical space. And they proposed an intuitive permeability model where you go from A to B, which is the water dissolved states in water, and B is the membrane dissolved states in the membrane. And then you get this dehydration penalty where you go from the membrane dissolved states in the membrane in water to the membrane dissolved states in the membrane. And again, the reverse reaction happens. Recently, Sugita et al., so they used molecular dynamic simulations with an enhanced sampling method called Repler exchange with umbrella sampling, and they simulated the entire membrane permeation event. Importantly, they found the presence of a barrier in the center of the membrane, which was not accounted for in previous models. So what we want to do, because MD simulations can be time intensive, we wanted a quick and generalizable model that could be used to predict membrane permeability for beyond rule of five macrocycles, especially for those existing outside of rule of five chemical space. And we wanted to use this model as sort of a high throughput sort of guide. And the model obviously had to use meaningful features. So we wanted to select features or variables to model the thermodynamic enthalpy and entropy of membrane permeation. and to use these physically meaningful features to improve the chances of a causative model. We say causative because all we have are correlations in the end, but we want the features to make sense, and we did that by modeling them based on the thermodynamics. The data set that we used for model generation, so we were aiming to use a machine learning model or random forest regression, and this is the data set. We split it into 3 subsets. So set 1 is a synthesis of peptide macrocycles from the literature, which have PAMPO values. So this PAP value is the permeation rate by an assay. Set 2 is the permeation rates originally reported by Over et al. In 2016. So there's 236 KCO2 PAP values by KCO2 assay. Set 3 peptides again, so peptide macrocycles, and there were 688 peptide macrocycles originally reported by Naylor et al. In 2018, and they look like this. So these are the structures. We combine these data sets, and the number of compounds with a non-zero PAP value were 800. So we used those for training the model. Just about the data sets. So we're going to use a machine learning model, specifically random forest regression, but the data set that we trained on was sets 1, 2, and 3, and the chemical space that the data set exists in is limited, in that the experimental log of PAP values ranged from -9 to 4. The molecular weight ranged from 400 to 960 grams per mole. The number of hydrogen bond donors ranged from 0 to 5. Number of hydrogen bond acceptors from 2 to 9. Polar surface area in water 60 to 220 angstrom squared. So this is the defined chemical space. These numbers in bold indicate that the macrocycles often exist outside of rule of 5 chemical space. And obviously, because we're training the model on this data, any prospective predictions that we make using the trained model might not be reliable if the macrocycles exist outside of that chemical space. So obviously, we're going to generate the model. To do that, we need features, and we generated a pool of features or variables by molecular modeling in hydrophobic and hydrophilic continuum solvents. And we also extracted features from SMILE strings. We removed highly correlated features by this criterion. So the R value was, the absolute value of the R value was greater than 0.95. Of these uncorrelated variables or features, we looked at which feature decreased the impurity of the decision tree the most. So that's the Gini importance metric, or GI. And of these features, so we picked the top 15 by GI. We looked at, we used some chemical intuition and picked 5 each to model the thermodynamic enthalpy and entropy of membrane permeation through a sort of more meaningful model. And then random forest regression was performed, and we generated the model using 6x10 fold cross validation. And I can explain that more probably in GatherTown, just in the interest of time. So here are the features we selected. And I'm going to introduce here something we're describing as the rule of 10. So if you follow these 10 rules, you maximize the chances of having a macrocycle with PAP greater than 1 × 10⁶ centimeters per second. So these 5 features underlined are the most important ones based on GI and R squared. And pretty much we want PSA in water, so polar surface area in water, to be between 118 and 175 angstrom squared. The octanol water partitioning coefficient, or A log P, generated from SMILES, we want that to be between 3 and 5. The number of hydrogen bond donors to be between 1 and 3, ideally. These features in red model enthalpy. These features in blue model entropy, and they have to do with the flexibility of the molecule. Just quickly, this one here is the topological distance between the nitrogen and oxygen atoms, and it has to be within that range to get a permeating macrocycle. And here, this is the topological distance between nitrogen atoms, and it has to be between 29 and 133. But these are the sum of the topological distances. So we use these 10 features for random forest regression model generation, and we get these results. So random forest regression, we get this nice straight line. That's the first thing you see in blue for the plot between experimental log of PAP and predicted log of PAP. For multilinear regression, we basically get not a straight line, or not really, because set 3 is poorly predicted by MLR, multilinear regression. By MLR, for the combined data set, we get an R squared of 0.28, that R squared is significant by the F score, and the RMSE is 5.61 fold. So that's the true experimental value will be plus or minus 5.61 fold for PAP than the predicted value. Similarly, for random forest regression validated by 6x10 fold cross validation, we get an R squared of 0.75, that the R squared is still significant, and the error between predicted, or the average error between predicted and experimental values, is lower, or 2.83 fold if we converted these to a linear scale. We can also conclude that the model is generalizable here because the predictions are only made on test data. That's how 6x10 fold cross validation works. So we wanted to additionally validate this model. So this is the model that was trained, tested, and validated on the training set of sets 1, set 2, and set 3. We applied this trained model to an additional validation data set, set 4, originally reported by Wang et al. And we get, for the Pamper data they report, we get a moderately reduced R squared of 0.53, so 53% of the variance in experiment is explained by the model. The F score indicates that the R squared is still significant. RMSE, the error goes up. But basically, we retain some level of predictive power in the trained model. Importantly, Wang et al. Reported multilinear regression models of our set 4, and they get an R squared of about 0.6, depending on which combination of experimental features we use. So given we're using purely theoretical features derived from a computer, the R squared 0.5, it's pretty good. So in summary, we've developed a predictive model using 10 meaningful features trained on over 800 macrocycles. We get R squared equals 0.75, and RMSE equals 2.83 using 6x10 fold cross validation. Predictions were only made on the trading data, so it's good. The top 5 features by GI and R squared were PSAW, A log P, number of hydrogen bond donors, the topological distance between nitrogen and nitrogen, so the sum of the topological distance, and the sum of the topological distance between nitrogen and oxygen. With the same underlying data, our model outperforms the 21 variable partial least squares regression model of set 2, or the data reported by Over et al. And yeah, so we've done pretty well, given we use only 10 features. The chemical space covered by our model is obviously this. So we want the data to be within this chemical space for our model to produce similar sorts of predictive power. So a word of caution, we observed a reduction in predictive power for set 4 to R squared equals 0.53, and the error goes up. This reduced predictive power is probably expected since sets 4 exist in different chemical space to the training data. So we just have to be careful how we apply machine learning. Acknowledgements. So the modeling group at MIPS, where I did my PhD, Monash and Parkville. The SBSB group, including Ray Norton, Nick Barlow, Maeda, and everyone. David, for being very patient with me during my PhD. Elizabeth, likewise. Ray, for having me on the project initially. Got to thank Monash University, NCI, Massive, and VLSCI for providing computing resources. So I'm now at RMIT as a postdoc. I have to thank Irene for taking me on board. So Professor Irene Yurovsky is very intelligent. She had the idea to use features that were that modeled entropy and enthalpy, so that's very good. I have to thank Lees in particular for this project for revising all the code written by Melissa Spear from the University of Melbourne. So yeah, she developed the machine learning models. Again, thanking computing resources, RMIT, and Melissa from the University of Melbourne. Sorry for going a bit over time. Are there any questions?
Thank you. Thank you, Billy, for a wonderful talk. In the interest of time, what we'll do, we'll request people to see you in Gather Town, and if they have any question, or they can reach out to you directly. And that brings us to the close of the current session. And please join me in thanking all our speakers for the machine learning session. So we have just a couple of announcements. We